Welcome to Math Kernel. Today we build the foundation of all the geometry in a vector space, the scalar product, and the length it hands you, the norm. Here are two vectors. On their own, they're just lists of numbers, an arrow's worth of data. No built-in length, and no notion of the angle between them.
Right? Nothing in the list of components says, this arrow is 3 long, or these two meet at 30 degrees. Geometry isn't free. Something has to supply it.
That something is the scalar product, the one extra ingredient that supplies both. For the ordinary vectors you know, it's almost embarrassingly simple. Multiply matching components and add them up.
Hold on. Multiply matching components and add is one specific recipe. Is that the definition or just one example of it? Why this rule and not some other?
Sharp, and it's exactly where we're headed. For now it's the standard one. By the end you'll see it's just one member of a whole family.
So what does that single number actually buy us?
Watch. A vector's product with itself is its length squared. Its product with a different vector hides the angle between them through cos theta. So one operation secretly carries both lengths and angles, the whole of Euclidean geometry, folded into a single number. Concretely, for these two, 3 times 1 plus 1 times 2 is 5. Over the next 20 minutes we'll meet the whole family, pin down the 3 rules they all obey, and learn the reflex for spotting a fake. Let's make that length claim precise, because it's really just Pythagoras wearing a disguise.
Pythagoras? We're in 3 dimensions with an abstract product now. How does the old a squared plus b squared sneak back in?
Watch it happen. Take a vector in 3 dimensions. Its product with itself is the sum of its squared components, 2 squared plus 2 squared plus 1 squared. Now read that sum as a picture. Walk along the first component, then the second, then the third. You've traced the edges of a box, and the vector is its long diagonal.
Oh, so the squared diagonal is the sum of the squared edges. It's Pythagoras applied one dimension at a time, stacking up the box.
Exactly. So the norm, the length, is defined as the square root of the product of x with itself. Here, the square root of 9, exactly 3.
Let me poke at that square root. You're taking the root of the product of x with itself. What guarantees that number is never negative, so the root is even real?
The best question in the whole video, hold on to it. The full answer is the third axiom, positive definiteness, and we'll make it the star later. For now, a real vector's product with itself is a sum of squares, so it can't be negative. I'm rotating the camera so you can see the length is an honest property of the vector, the same from every side, not an accident of the viewpoint.
And it genuinely doesn't change as it turns. The 3 is baked into the arrow, not into where we're standing.
One fact we'll reuse constantly. Scaling a vector by a factor alpha scales its length by the absolute value of alpha. Double the arrow, and its norm doubles. So, length falls straight out of the product. It's just Pythagoras in n dimensions, and it scales exactly the way a length should. Here's the thing most people miss on a first pass. The standard dot product is not the only scalar product. It's just the most symmetric one.
Meaning what exactly? If I go and change the recipe, don't I just get something that isn't a scalar product anymore?
Not necessarily. Suppose some directions matter more than others. Give each coordinate its own positive weight, and define the product as that weighted sum, w1 x1 y1, plus w2 x2 y2, and so on.
So it's the same multiply and add, but each term gets a dial turned up or down.
Exactly. And is it still legitimate? Check the rule that matters. A vector with itself becomes a sum of each weight times its own component squared. Every weight is positive, so that sum is at least 0, and it's 0 only when the vector itself is 0.
And if I sneaked in a negative weight?
Then it collapses, you'd get a direction with negative length squared, and it's no longer a scalar product. The positivity of every weight is exactly what keeps it honest.
What does weighting do to the shape of the space itself?
It reshapes what length 1 means. Put weight 4 on the second coordinate, and the y direction costs more, so the set of unit vectors is no longer a circle, it's an ellipse squashed in y. Same 3 rules, a brand new geometry. Turn the weights, and you've changed the very meaning of distance and angle. Both of those, the standard product and the weighted one, are secretly the same construction. Sandwich a matrix M between the two vectors, xᵀM, y. That one formula is the general recipe.
A matrix in the middle. So the matrix is the thing that decides which geometry we're living in.
Precisely. Take M to be the identity, and the sandwich collapses back to the plane dot product. Take M diagonal, with the weights down the diagonal, and you recover the weighted product. So identity and weighted aren't two separate ideas, they're two settings of the same dial, M.
Then can I drop any matrix into the middle and call the result a scalar product?
No, and that's the crucial restriction. For xᵀM y to be a genuine scalar product, M has to be symmetric, equal to its own transpose, and positive definite. xTM x positive for every non-zero x.
Symmetric and positive definite. That sounds like the checklist you keep promising.
It is exactly the checklist. Keep it in your pocket. It becomes the exam reflex in a few minutes.
Do the off-diagonal entries actually show up in the picture, or are they just bookkeeping?
Very visible. Here both off-diagonals are 1, and that coupling ties the two coordinates together, so the unit ellipse tilts, its axis rotating off the grid to 45 degrees along the eigenvectors of M. One recipe, one matrix, identity, diagonal, or fully coupled, M encodes the entire geometry of the space. Here's the leap that makes linear algebra feel infinite. The vectors don't have to be arrows at all, they can be functions.
Functions as vectors, how am I supposed to picture the length of a function?
Start from what the dot product does, run over the components, multiply pairwise, sum. Now think of a function as a vector with infinitely many components, one value for every point x. Replace the sum over components with an integral over x, and the scalar product of f and g is the integral of f times g.
Infinitely many components, and you just swap the sum for an integral? Does every rule really survive that jump?
The one that matters does. A function with itself is the integral of f squared, the continuous echo of sum of the squares. It's an area, and since the integrand is a square, that area can't be negative.
So a function's length is just the square root of that area.
Exactly. The blue line is f of x equals x, and the green region is the integral of its square, its norm, squared. So the whole framework, lengths, angles, projections, never cares whether a vector is an arrow or a function. And that one idea, that functions live in a space with lengths and angles, is the doorway to Fourier series, big enough that it earns its own video later in the chapter. Now push into complex vector spaces, and one axiom needs a small repair.
Why should anything change? Symmetry worked perfectly well a minute ago.
Because over the complex numbers, plane symmetry breaks length. If the product of x with itself could be any complex number, its square root, the length, would be complex, which is nonsense. So we replace symmetry with conjugate symmetry. Swapping the arguments conjugates the value.
Conjugate, so swapping the order reflects the value across the real axis.
Right. Now set the two arguments equal and watch the rescue. Conjugate symmetry says the product of x with itself equals its own conjugate, and a number equal to its own conjugate has no imaginary part.
A number that equals its own conjugate is forced to be real.
forced onto the real axis. And because it's real and positive definiteness makes it positive, the square root is an ordinary real length again. The norm is saved, you just needed the conjugate to keep it honest. Real or complex, the point never changes. Whatever twist symmetry takes, it exists to keep a vector's product with itself a genuine, non-negative length. Strip away the examples, vectors, weights, matrices, functions, and every scalar product is exactly the same three rules. This is the definition. First, bilinearity. It's linear in each slot separately. Pull scalars out, split sums apart. Scale x, and the product scales the same way.
So this is the rule that lets us expand a product like an ordinary bracket.
Exactly, it's the workhorse. Almost every proof in the next two videos begins by expanding with bilinearity. Second, symmetry. The order of the two arguments doesn't matter.
That one feels almost too obvious to write down. Does it really earn its place?
It earns it quietly. With linearity in the first slot plus symmetry, linearity in the second slot comes for free, one axiom doing double duty. Third, the subtle one, positive definiteness. A vector's product with itself is never negative, and it's zero for exactly one vector, the zero vector.
This is the one guy keeps circling back to, the length guarantee.
It is. And here's its precise job. It's what makes the square root in the norm legal. The product of x with itself is at least zero, so its root is real, and it vanishes only for the zero vector, so only the origin has length 0. Bilinear, symmetric, positive definite. Every scalar product you'll ever meet is just those three demands wearing a costume. Now the reflex the exam is really testing. You're handed a formula and asked, is this a scalar product? You walk the three axioms in order, and here the matrix M is already an old friend.
Same M as the tilted ellipse. So where do I even start? Do I have to check all three from scratch every single time?
You go in order, and the first two are quick. Because it's in matrix form, bilinearity is automatic. Matrix vector multiplication is linear. First axiom, free. Symmetry is just a glance. Is M equal to its transpose? Mirror the entries across the diagonal, the 1 and the 1 match. Second axiom, done.
So all the real content lives in the third axiom.
It does, and it has a beautiful shape. Write the product of x with itself as a quadratic, 2x1 squared, plus 2x1x2, plus 2x2 squared, and picture its graph, this bowl.
A bowl is suggestive, but a picture isn't a proof. How do I know it never dips below 0 somewhere I can't quite see?
You complete the square. 2 times x1 plus half x2 squared plus 3 halves x2 squared. Both terms are squares, so the whole surface sits on or above the floor. The picture, now proven. And it touches 0 at exactly one point, the origin, and is positive everywhere else. That's positive definiteness, made visible. All three axioms hold, so yes, a genuine scalar product. Checklist passed. Matrix form gives bilinear, a symmetric M gives symmetry, and the bowl gives positive definite. Scalar product, confirmed. I'm turning the bowl so you can confirm it from every side. No matter where you look, it never drops below the floor. There is no way to get a negative length here. Now the other side of the reflex, how to shoot one down. Here's a candidate, the diagonal matrix with a -1.
This one's symmetric too. Doesn't it sail through the first two axioms just like the last one did?
It does, bilinear and symmetric, both fine. And that's the trap. Stop there, and you'd wrongly call it a scalar product.
So the crime has to be in the third axiom again, the length rule.
Look at its quadratic form, x1 squared minus x2 squared. That minus sign changes everything. The graph isn't a bowl, it's a saddle, rising one way and falling the other, straight through the floor.
And anywhere the surface drops below the floor, the product of x with itself is negative.
A negative length squared, which a real scalar product can never allow.
Then let me make the objection concrete. Don't just say it fails, which vector actually breaks it.
That's the right instinct, and it earns the marks. Name the witness. Along E2, the form is 0, -1, -1. A concrete vector where positive definiteness visibly fails. So the verdict, bilinear yes, symmetric yes, positive definite no, not a scalar product. And here's the very vector that proves it. That's the whole habit. A bowl passes, a saddle fails. And when the answer is no, you always hand over the specific vector, like E2, that breaks the axiom. Let's gather it up. A scalar product is any rule sending two vectors to a number that's bilinear, symmetric, and positive definite.
And each valid choice draws its own unit circle, a circle, an axis-aligned ellipse, a tilted one, even one made of functions.
From any of them you get length for free. The norm is the square root of a vector's product with itself, and positive definiteness is exactly what keeps that root real and honest.
And the exam reflex so I don't drop marks?
Given a candidate, check the three axioms in order, and if one fails, name the vector that breaks it. A bull passes, a saddle fails. Next, we squeeze the geometry back out of these axioms. The Cauchy-Schwarz inequality, the true angle between two vectors, and why the triangle inequality is forced to hold. That's the scalar product, and the norm it hands you, three axioms, one whole idea of geometry. Thanks for watching. Next time, Cauchy-Schwarz, and the geometry it unlocks. See you in the next one.